In Chapter 2, we're going to talk about the following concepts. We're going to discuss fields, methods, constructors, parameters, and the assignment statement, as well as conditional statements. In this chapter, we take our first look at the source code of a class. We will discuss the basic elements of class definitions, such as fields, constructors, and methods. Methods contain statements, and initially, we look at methods containing only simple arithmetic and printing statements. But later, we introduce conditional statements that allow choices between different actions to be made within the methods. We shall start by examining a new project in a fair amount of detail. This project represents a naive implementation of an automated ticket machine. As we start by introducing the most basic features of classes, we shall quickly find that this implementation is deficient in a number of ways. So we shall proceed to describe a more sophisticated version of the ticket machine that represents a significant improvement. And finally, in order to reinforce the concepts introduced in this chapter, we take a look at the internals of the lab classes example encountered in the previous chapter, Chapter 1. So, train stations often provide ticket machines that print a ticket when a customer inserts the correct money for their fare. In this chapter, we shall define a class that models something like these ticket machines. As we shall be looking inside our first Java example classes, we shall keep our simulation fairly simple to start with. And this will give us the opportunity to ask some questions about how these models differ from the real-life versions, and how we might change our classes to make the objects they create more like the real thing. Our ticket machines work by customers inserting money into them, and then requesting a ticket to be printed. Each machine keeps a running total of the amount of money it has collected throughout its operation. In real life, it is often the case that a ticket machine offers a selection of different types of tickets, from which the customers choose the one they want. Our simplified machines, however, print tickets of only a single price. It turns out to be significantly more complicated to program a class to be able to issue tickets of different values than it does to offer a single price. On the other hand, with object-oriented programming, it is very easy to create multiple instances of the class, each with its own price setting, to fulfill a need for different types of tickets. So let's open the naive ticket machine project in BlueJ. This project contains only one class, which is ticket machine, which you'll be able to explore in a similar way to the examples that we discussed in the previous chapter. And when you create the ticket machine instance, you'll be asked to supply a number that corresponds to the price of tickets that will be issued by that particular machine. And this price is taken to be a number of cents. So a positive whole number, such as 500, would be appropriate as a value to work with. So why don't you create a ticket machine object on the object bench and take a look at its methods? You should see the following: get balance, get price, insert money, and print ticket. So try out the get price method. You should see a return value containing the price of the tickets that was sent when this object was created. Use the insert money method to simulate inserting an amount of money into the machine. Okay, so feel free to pause this video here and have a go at some of the exercises displayed on the screen. And then once you've had a go, click resume and we'll have a look at the next section. So the exercises at the end of the previous section reveal that the ticket machine objects only behave in the way that we expect them to if we insert the exact amount of money to match the price of the ticket. As we explore the internal details of the class in this section, we shall see why this is so. Take a look at the source code for the ticket machine class by double-clicking on its icon in the class diagram within BlueJ. And it should look something like that displayed here. For reference, this is the complete text of the class here. And by looking at the text of the class definition piece by piece, we can flesh out some of the object-oriented concepts that we discussed previously in Chapter 1. This class definition contains many of the features of Java that we will see over and over again, so it will pay greatly to study it carefully. The text of a class can be broken down into two main parts. A smaller outer wrapping that simply names the class, appearing on a green background, and a much larger inner part that does all of the work. In this case, the outer wrapping appears as follows: public class, ticket machine, and then we would have code enclosed within the pairs of curly braces here. So the outer wrappings of different classes all look much the same. The outer wrapping contains the class header, whose main purpose is to provide a name for the class. By a widely followed convention, we always start class names with an uppercase letter. As long as it is used consistently, this convention allows class names to be easily distinguished from other sorts of names, such as variable names and method names, which will be described shortly. And above the class header is a comment, shown here as blue text, that tells us something about the class. The words public and class are part of the Java language, whereas the word ticket machine is not. The person writing the class has chosen that particular name. We call words like public and class keywords or reserved words. The terms are used frequently and interchangeably. There are around 50 of these in Java, and you will soon be able to recognize most of them. A point worth remembering is that Java keywords never contain uppercase letters, whereas the words which we get to choose, like ticket machine, are often a mix of upper and lowercase letters. The inner part of the class is where we define the fields, constructors, and methods that give the objects of that class their own particular characteristics and behavior. We can summarize the essential features of these three components of a class as follows. The fields store data persistently within an object. The constructors are responsible for ensuring that an object is set up properly when it is first created. And the methods implement the behavior of an object. They provide its functionality. In BlueJ, fields are shown as text on a white background, while constructors and methods are displayed as yellow boxes. In Java, there are very few rules about the order in which you can choose to define the fields, constructors, and methods within a class. In the ticket machine class, we have chosen to list the fields first, the constructors second, and finally the methods. This is the order that we shall follow in all of our examples. Other authors choose to adopt different styles, and this is mostly a question of preference. Our style is not necessarily better than all the others. However, it is important to choose one style and then use it consistently, because then all of your classes will be easier to read and understand. So, fields store data persistently within an object. The ticket machine class has three fields: price, balance, and total. Fields are also known as instance variables because the word variable is used as a general term for things that store data in a program. We have defined the fields right at the start of the class definition. All of these variables are associated with monetary items that a ticket machine object has to deal with. Price stores the fixed price of a ticket. Balance stores the amount of money inserted into the machine by a user prior to asking for a ticket to be printed. And total stores the total amount of money inserted into the machine by all of the users since that machine object was constructed, excluding any current balance. The idea is that when the ticket is printed, any money in the balance is transferred to the total. Fields are small amounts of space inside an object, that can be used to store data persistently. Every object will have space for each field declared in its class. And here we see a diagrammatic representation of a ticket machine object with its 3 fields. The fields have not yet been assigned any values. Once they have, we can write each value into the box representing the field. The notion is similar to that used in BlueJ to show objects on an object bench, except that we show a bit more detail here. In BlueJ, for space reasons, the fields are not displayed on the object icon. But we can, however, see them by opening an inspector window. Each field has its own declaration in the source code. On the line above each, in the full class definition, we have added a single line of text, a comment, for the benefit of human readers of the class definition, as you can see here. A single line comment is introduced by 2 characters, the 2 forward slashes, which are written with no spaces in between them. More detailed comments, often spanning several lines, are usually written in the form of multi-line comments. And these start with the character pair, which is / followed by an asterisk, and then end with the pair */. And there is a good example of this preceding the header of the class. And we can see that the definitions of the 3 fields are quite similar. All the definitions indicate that they are private fields of the object. We shall have more to say about what this means in Chapter 6, but for the time being, we shall simply say that we always define fields to be private. All 3 fields are of type int. An int is another keyword and represents the data type integer. This indicates that each can store a single whole number value, which is reasonable given that we wish them to store numbers that represent amounts of money in cents. Fields can store values that can vary over time, so they are also known as variables. The value stored in a field can be changed from its initial value if required. For instance, as more money is inserted into a ticket machine, we shall want to change the value stored in the balance field. It is common to have fields whose values change often, such as balance and total, and others that change rarely or not at all, such as price. The fact that the value of price doesn't vary, once set, does not alter the fact that it is still called a variable. In the following sections, we shall also meet other kinds of variables in addition to fields, but they will all share the same fundamental purpose of storing data. The price, balance, and total fields are all the data items that a ticket machine object needs to fulfill its role of receiving money from a customer, printing tickets, and keeping a running total of all the money that has been put into it. In the following sections, we shall see how the constructor and methods use those fields to implement the behavior of naive ticket machines. From the definitions of fields we have seen so far, we can begin to put together a pattern that will apply whenever we define a field variable in a class. They usually start with the reserved word private. They usually include a type name, such as int, string, person, etc. They include a user-chosen name for the field variable, and they end with a semicolon. So remembering this pattern will help you when you come to write your own classes. Indeed, as we look closely at the source code of different classes, you will see patterns such as this one emerging over and over again. Part of the process of learning to program involves looking out for such patterns and then using them in your own programs. That is one reason why studying source code in detail is so useful at this stage. Constructors have a special role to fulfill. They are responsible for ensuring that an object is set up properly when it's first created. In other words, for ensuring that an object is ready to be used immediately following its creation. This construction process is also called initialization. In some respects, a constructor can be likened to a midwife. It is responsible for ensuring that the new object comes into existence properly. Once an object has been created, the constructor plays no further role in that object's life and cannot be called again. And here we see the constructor of the ticket machine class. One of the distinguishing features of constructors is that they have the same name as the class in which they are defined, ticket machine in this case. The constructor's name immediately follows the word public, with nothing in between. We should expect a close connection between what happens in the body of the constructor and the fields of the class. This is because one of the main roles of the constructor is to initialize the fields. It will be possible with some methods, such as balance and total, to set sensible initial values by assigning a constant number, 0 in this case. With others, such as the ticket price, it's not that simple, as we do not know the price that the tickets for a particular machine will have until that machine is constructed. Recall that we might wish to create multiple machine objects to sell tickets with different prices, so no one initial price will always be right. You will know from experimenting with creating ticket machine objects within BlueJ that you had to supply the cost of the tickets whenever you created a new ticket machine. An important point to note here is that the price of a ticket is initially determined externally and then has to be passed into the constructor. And within BlueJ, you decide the value and then enter it into the dialog box. Part of the task of the constructor is to receive that value and store it in the price field of the newly created ticket machine so that the machine can remember what the value was without you having to keep reminding it. We can see from this that one of the most important roles of a field is to remember external information passed into the object, so that that information is available to an object throughout its lifetime. Fields, therefore, provide a place to store long-lasting, or in other words, persistent data. And here we see a ticket machine object after the constructor has executed. Values have now been assigned to the fields, and from this diagram we can tell that the ticket machine was created by passing in 500 as the value for the ticket price. In the next section, we discuss how values are received by an object from outside. Constructors and methods play quite different roles in the life of an object. But the way in which both receive values from outside is the same, via parameters. You may recall that we briefly encountered parameters in Chapter 1, Section 1.4. Parameters are another sort of variable, just as fields are, so they are also used to hold data. Parameters are variables that are defined in the header of a constructor or a method, as you can see here. This constructor has a single parameter, cost, which is of type int, the same type as the price field it will be used to set. A parameter is used as a sort of temporary messenger, carrying data originating from outside the constructor or method and making it available inside it. And here we see how values are passed via parameters. In this case, a BlueJ user enters the external value into the dialog box when creating a new ticket machine, shown here. And that value is then copied into the cost parameter of the new machine's constructor. This is illustrated with the arrow labelled A. The box in the ticket machine object, here, labelled ticket machine, in brackets constructor, represents additional space for the object that is created only when the constructor executes. We shall call it the constructor space of the object, or method space when we talk about methods instead of constructors, as the situation there is the same. The constructor space is used to provide space to store the values for the constructor's parameters. In our diagrams, all variables are represented by white boxes. We distinguish between the parameter names inside a constructor or method and the parameter values outside by referring to the names as formal parameters and the values as actual parameters. So cost is a formal parameter and the user supplied value, such as 500, is an actual parameter. A formal parameter is available to an object only within the body of a constructor or a method that declares it. We say that the scope of a parameter is restricted to the body of the constructor or the method in which it is declared. In contrast, the scope of a field is the whole of the class definition. It can be accessed from anywhere in the same class. This is a very important difference between these two sorts of variables. A concept related to the variable scope is the variable lifetime. The lifetime of a parameter is limited to a single call of a constructor or method. When a constructor or method is called, the extra space for the parameter variables is created, and the external values are copied into that space. Once that call has completed its task, the formal parameters disappear, and the values they held are lost. In other words, when a constructor has finished executing, the whole constructor space is removed, along with the parameter variables held within it. In contrast, the lifetime of a field is the same as the lifetime of the object to which it belongs. When an object is created, so are the fields, and they persist for the lifetime of that object. It follows that if we want to remember the cost of the tickets held in the cost parameter, we must store the value somewhere persistent, that is, in the price field. Just as we expect to see a close link between the constructor and the fields of its class, we expect to see a close link between the constructor's parameters and the fields, because external values will often be needed to set the initial values of one or more of those fields. Where this is the case, the parameter types will closely match the types of the corresponding fields. One of the things you might have noticed is that the variable names we use for fields and parameters have a close connection with the purpose of the variable. Names such as price, cost, title, and alive all tell you something useful about the information being stored in that variable. This makes it easier to understand what is going on in the program. Given that we have a large degree of freedom in our choice of variable names, it is worth following this principle of choosing names that communicate a sense of purpose, rather than arbitrary and meaningless combinations of letters and numbers. In the previous section, we noted the need to copy the short-lived value stored in this parameter variable into somewhere more permanent, a field variable. In order to do this, the body of the constructor contains the following assignment statement. Assignment statements are used frequently in programming as a means to store a value into a variable. They can be recognized by the presence of an assignment operator, such as an equals sign shown in the example here. Assignment statements work by taking the value of what appears on the right-hand side of the operator and copying that value into the variable on the left-hand side. The right-hand side is called an expression. In their most general form, expressions are things that compute values. But in this case, an expression consists of just a single variable, whose value is copied into the price variable. We shall see examples of more complicated expressions later in this chapter. One rule about assignment statements is that the type of the expression on the right-hand side must match the type of the variable to which its value is assigned. We've already met 3 different but commonly used types, such as int, string, and also, very briefly, Boolean. This rule means that we are not allowed to store an int type expression in a string type variable. And this rule means that we are not allowed to store an int type expression in a string type variable, for instance. This same rule also applies between formal parameters and actual parameters. The type of an actual parameter expression must match the type of the formal parameter variable. For now, we can say that the types of both must be the same, although we shall see in later chapters that this is not the whole truth. The ticket machine class has 4 methods: getPrice, getBalance, insertMoney, and printTicket. You can see them in the class's source code as yellow boxes. We shall start looking at our source code of methods by considering the getPrice method. Methods have 2 parts, a header and a body. Here is the method header for getPrice, preceded by a descriptive comment. It is important to distinguish between the method headers and the field declarations, because they can look quite similar. We can tell that getPrice is a method and not a field because the method headers always include a pair of parentheses, that is, an opening bracket and a closing bracket, and no semicolon at the end of the header. The method body is the remainder of the method after the header. It is always enclosed by a matching pair of curly braces, or otherwise known as squiggly brackets. Method bodies contain the declarations and statements that define what an object does when that method is called. Declarations are used to create additional temporary variable space, while statements describe the actions of the method. In getPrice, the method body contains a single statement, but we shall soon see examples where the method body consists of many lines of both declarations and statements. Any set of declarations and statements between a pair of matching curly braces is known as a block. So the body of the ticket machine class, the bodies of the constructor, and all of the methods within the class are blocks. There are at least 2 significant differences between the headers of the ticket machine constructor and the getPrice method. The method has a return type of int, but the constructor has no return type. A return type is written just before the method name. This is the difference that applies in all cases. The constructor has a single formal parameter, cost, but the method has none, just a pair of empty parentheses. And this is the difference that applies in this particular case. It is an absolute rule in Java that a constructor may not have a return type. On the other hand, both constructors and methods may have any number of formal parameters, including none. Within the body of the getPrice method, there is a single statement, return price. This is called a return statement. It is responsible for returning an integer value to match the int return type in the method's header. Where a method contains a return statement, it is always the final statement of that method, because no further statements in that method will be executed once the return statement is executed. Return types and return statements work together. The int return type of getPrice is a form of promise that the body of the method will do something that ultimately results in an integer value being calculated and returned as the method's result. You might like to think of a method call as being a form of question to an object, and the return value from the method being the object's answer to that question. In this case, when the getPrice method is called on a ticket machine, the question is, what do tickets cost? A ticket machine does not need to perform any calculations to be able to answer that, because it keeps the answer in its price field. So the method answers by just returning the value of that variable. As we gradually develop more complex classes, we shall inevitably encounter more complex questions that require more work to supply their answers. We often describe methods such as the 2 get methods of ticket machine, which are getPrice and getBalance, as accessor methods, or just accessors. This is because they return information to the caller about the state of the object. They provide access to information about the object's state. An accessor usually contains a return statement in order to pass back that information. There is often confusion about what returning a value actually means in practice. People often think it means that something is printed by the program, and this is not the case at all. We shall see how printing is done when we have a look at the print ticket method. Rather, returning a value means that some information is passed internally between two different parts of the program. One part of the program has requested information from an object via a method call, and the return value is the way the object has of passing that information back to the caller. The get methods of a ticket machine perform similar tasks, returning the value of one of their object's fields. The remaining methods, insert money and print ticket, have a much more significant role, primarily because they change the value of one or more fields of the ticket machine object each time they're called. We call methods that change the state of their object mutator methods, or just mutators. In the same way as we think of a call to an accessor as a request for information, a question, we can think of a call to a mutator as a request for an object to change its state. The most basic form of a mutator is one that takes a single parameter whose value is used to directly overwrite what is stored in one of an object's fields. In a direct complement to the get methods, these are often called set methods, although the ticket machine does not have any of those at this stage. One distinguishing effect of a mutator is that an object will often exhibit slightly different behavior before and after it's called, and we can illustrate this with the following exercise. So why don't you create a ticket machine with a ticket price of your choosing, and before doing anything else, call the getBalance method on it. Now call the insertMoney method and give it a non-zero positive amount of money as the actual parameter. And now call the getBalance again. The two calls to the getBalance method should show slightly different outputs because the call to insert money has had an effect on changing the machine's state via its balance field. The header of the insert money method has a void return type and a single formal parameter, amount, of type int. A void return type means that the method does not return any value to its caller. This is significantly different from all other return types. Within BlueJ, the difference is most noticeable in that no return value dialog is shown following a call to a void method. Within the body of a void method, this difference is reflected in the fact that there is no return statement. In the body of insert money, there is a single statement that is another form of the assignment statement. We always consider assignment statements by first examining the calculation on the right-hand side of the assignment symbol. Here, its effect is to calculate a value that is the sum of the number in the amount parameter and the number in the balance field. This combined value is then assigned to the balance field, so the effect is to increase the value in balance by the value in amount. Here, we see the most complex method of the class, which is print ticket. To help your understanding of the following discussion, make sure that you have called this method on a ticket machine, and you should have seen something like the following printed in the BlueJ terminal window. This is the longest method that we've seen so far, so we'll break it down into more manageable pieces. The header indicates that the method has a void return type, and that it has no parameters. The body comprises of 8 statements plus associated comments. The first 6 statements are responsible for printing what you see in the BlueJ terminal window, which is 5 lines of text and a 6th blank line. The 7th statement adds the balance inserted by the customer through previous calls to insert money to the running total of all money collected so far by the machine. The 8th statement resets the balance to 0 with a basic assignment statement in preparation for the next customer. By comparing the output that appears with the statements that produced it, it is easy to see that a statement such as system.out.println literally prints the string that appears between the matching pair of double quotes characters. The basic form of a call to println is system.out.println something we want to print, where something we want to print can be replaced with any arbitrary string enclosed with a pair of speech marks or double quotes. For instance, there is nothing significant in the hash character that is in the string. It is simply one of the characters that we wish to print. All of the printing statements in the print ticket method are calls to the println method of the system.out object that is built into the Java language, and what appears between the round brackets is the parameter to each method call, as you might expect. However, in the 4th statement, the actual parameter to println is a little more complicated and requires some more explanation. What it does is to print out the price of the ticket with some extra characters on either side of the amount. The 2 plus sign operators are being used to construct a single actual parameter in the form of a string from 3 separate components. The string literal, which is the hash, note the space character after the hash as well, the value of the price field, and note that there are no quotes around the field name because we want the field's value, not the name. And then finally, the string literal, which is cents. And again, note the space character before the word cents. When used between a string and anything else, the plus sign is a string concatenation operator, i.e. it concatenates, or in other words, joins strings together to create a new string, rather than an arithmetic addition operator. So the numeric value of price is converted into a string and joined to its 2 surrounding strings. And note that the final call to println contains no string parameter. This is allowed, and the result of calling it will be to leave a blank line between this output and any that follows after. And you will easily see a blank line if you print a second ticket. It is worth summarizing a few features of methods at this point, because methods are fundamental to the programs we will be writing and exploring in this book. They implement the core actions of every object. A method with parameters will receive data passed to it from the method's caller, and will then use that data to help it perform a particular task. However, not all methods take parameters. Many simply use the data stored within the object's fields to carry out their task. If a method has a non-void return type, it will return some data to the place it was called from. And that data will almost certainly be used in the caller for further calculations or program manipulations. Many methods, though, have a void return type and return nothing, but they still perform a useful task within the context of their object. Accessor methods have non-void return types and return information about the object's state, whereas mutator methods modify an object's state. Mutators often take parameters whose values are used in the modification, although it is still possible to write a mutating method that does not take parameters. We have now examined the internal structure of the naive ticket machine class in some detail. We have seen that the class has a small outer layer that gives a name to the class, and a more substantial inner body containing fields, a constructor, and several methods. Constructors are used to set up an initial state when an object is created. Having a proper initial state will enable an object to respond appropriately to method calls immediately following its creation. And methods implement the defined behavior of the class's objects. Accessor methods provide information about an object state, and Mutator methods change an object state. We have seen that constructors are distinguished from methods by having the same name as the class in which they're defined. Both constructors and methods may take parameters, but only methods have a return type. Non-void return types allow us to pass a value out of a method to the place where the method was called from. A method with a non-void return type must have at least one return statement in its body, and this will often be the final statement. Constructors never have a return type of any sort, not even void. So as we've now covered quite a lot of new concepts, have a go at the following exercises. Start by modifying the constructor of ticket machine so that it no longer has a parameter. Instead, the price of tickets should be fixed at 1,000 cents. And so what effect does this have when you construct ticket machine objects within BlueJ? So take a few minutes to have a go at the following exercises. Feel free to pause the video here, and then we'll continue after you've had a go at these exercises. So now that we've had a go at these exercises, let's move on and have a think about a different design for our ticket machine. Okay, so from our study of the internals of the ticket machine class, you should have come to appreciate how inadequate it would be in the real world. It's deficient in several ways. It contains no check that the customer has entered enough money to pay for the ticket. It also doesn't refund any money if the customer has paid too much for a ticket. It doesn't check to ensure that the customer inserts sensible amounts of money. And for instance, experiment what happens if a negative amount is entered. And finally, it doesn't check that the ticket price passed to the constructor is sensible. So if we could remedy these problems, then we would have a much more functional piece of software that might serve as the basis for operating a real-world ticket machine. In the next few sections, we shall examine the implementation of an improved ticket machine class that attempts to deal with some of the inadequacies of the naive implementation. So why don't you open the Better Ticket Machine project? And as before, this project contains a single class, which is ticket machine. But before looking at the internal details of the class, experiment with it by creating some instances and see whether you notice any differences in behavior between this version and the previous naive version. One specific difference is that the new version has an additional method called refund balance. Why not take a look and see what happens when you call it? So the code shown here shows the internal details of the Better Ticket Machines class definition. Much of this definition will already be familiar to you from our discussion of the naive ticket machine. For instance, the outer wrapping that names the class is the same because we have chosen to give this class the same name. In addition, it contains the same free fields to maintain the object's state, and these have also been declared in the same way. And the constructor and the two get methods are also the same as before. However, the first significant change can be seen in the insert money method. We recognize that the main problem with the naive ticket machine was its failure to check certain conditions. One of those missing checks was on the amount of money inserted by the customer, as it was possible for a negative amount of money to be inserted. We've remedied that failing by making use of a conditional statement to check that the amount of money inserted has a value greater than 0, as can be seen here. Conditional statements are also known as if statements, from the key word used in most programming languages to introduce them. A conditional statement allows us to take one of two possible actions based upon the result of a check or a test. If the test is true, then we do one thing, otherwise we do something different. And this kind of either-or decision should be familiar from situations in everyday life. For instance, if I have enough money left, then I shall go out for a meal. Otherwise, I shall stay at home and watch a movie. And a conditional statement has the general form described with the following pseudocode, as shown here. Certain parts of this pseudocode are proper bits of Java, and those will appear in almost all conditional statements. The keywords if and else, the round brackets around the test, and the curly brackets marking the two blocks. While the other three italicized parts will be fleshed out differently for each particular situation being coded. Only one of the two blocks of statements following the test will ever be performed, following the evaluation of the test. So, in the example from the insert money method, following the test of an inserted amount, we shall only either add the amount to the balance or print the error message. The test uses the greater than operator, which is the arrow pointing right, to compare the value in amount against 0. If the value is greater than 0, then it is added to the balance. If it is not greater than 0, then an error message is printed. By using the conditional statement, we have, in effect, protected the change to balance in the case where the parameter does not represent a valid amount. And if you're interested in finding out more, details of other Java operators can be found in Appendix C. The obvious ones to mention at this point are the less than operator, the less than or equal to operator, and also greater than or equal to. And all of these are used to compare two numeric values, as is the case in the print ticket method. The test used in a conditional statement is an example of a Boolean expression. Earlier in this chapter, we introduced arithmetic expressions that produced numerical results. A Boolean expression has only two values, true or false. The value of amount is either greater than 0, which is true, or it is not greater, which would be false. Therefore, a conditional statement makes use of these two possible values to choose between two different actions. The print ticket method contains a further example of a conditional statement. Here it is in outline. With this if statement, we fixed the problem that the naive version had, where it made no check to see whether the customer had inserted enough money for a ticket before printing. Whereas this version checks that the value in the balance field is at least as large as the value in the price field. And if it is, then it's okay to print a ticket. If it's not, then we print an error message instead. The printing of an error message follows exactly the same pattern as we saw for printing the price of tickets in the print ticket method. It's just a little bit more verbose. The single actual parameter to the printline method consists of a concatenation of three elements, which are two string literals on either side of a numeric value. In this case, the numeric value is a subtraction that has been placed in parentheses to indicate that it is the resulting value we wish to concatenate with the two strings. The printline method reduces the value of balance by the value of price. As a consequence, if a customer inserts more money than the price of the ticket, then some money will be left in the balance that could be used towards the price of a second ticket. Alternatively, the customer could ask to be refunded the remaining balance, and that is what the refund balance method does, as we shall soon see in section 2.16. You will have noticed by now that the BlueJ editor displays source code with some additional decoration, which are coloured boxes around some elements, such as methods and if statements. These coloured annotations are known as scope highlighting, and they can help clarify logical units of your program. A scope, also called a block, is a unit of code usually indicated by a pair of curly brackets. The whole body of a class is a scope, as is the body of each method and the if and else parts of an if statement. As you can see, scopes are often nested. The if statement is inside a method, which is inside a class. And BlueJ helps by distinguishing different kinds of scopes with different colours. One of the most common errors in the code of beginning programmers is getting the curly brackets wrong, either by having them in the wrong place or by having a bracket missing altogether. And there are two things that can greatly help in avoiding this kind of error. Firstly, pay attention to proper indentation of your code. Every time a new scope starts, after an open curly bracket, indent the following code one more level. Closing the scope brings the indentation back, but if your indentation is completely out, use BlueJ's auto layout function to fix it, and you can find this in the editor menu. And secondly, pay attention to the scope highlighting. You will quickly get used to the way in which well-structured code looks. And try removing a curly bracket in the editor or adding one in an arbitrary location and observe how the colouring changes. Get used to recognizing when scopes look wrong. So far, we have encountered two different sorts of variables: fields, otherwise known as instance variables, and parameters. We are now going to introduce a third kind. All have in common that they store data, but each sort of variable has a particular role to play. Section 2.7 noted that a method body, or more generally, a block, can contain both declarations and statements. To this point, none of the methods we have looked at contain any declarations. The refund balance method contains 3 statements and a single declaration. The declaration introduces a new kind of variable, as we can see here. What sort of variable is amount to refund? We know that it is not a field because fields are defined outside methods. It's also not a parameter, as those are always defined in the method header. The amount to refund variable, therefore, is what is known as a local variable, because it is defined inside a method body. Local variable declarations look similar to field declarations, but they never have private or public as part of them. Constructors can also have local variables. Like formal parameters, local variables have a scope that is limited to the statements of the method to which they belong. Their lifetime is the time of the method execution. They are created when a method is called and then destroyed when a method finishes. You might wonder why there is a need for local variables if we have fields. Local variables are primarily used as temporary storage to help a single method complete its task. We think of them as data storage for a single method. In contrast, fields are used to store data that persists through the life of a whole object. The data stored in fields is accessible to all of the object's methods. We try to avoid declaring as fields variables that only have a local, or in other words, method level usage, whose values don't have to be retained beyond a single method call. So even if 2 or more methods in the same class use local variables for a similar purpose, it is not appropriate to define them as fields if their values do not need to persist beyond the end of the methods. In the refund balance method, amount to refund is used briefly to hold the value of the balance immediately prior to the latter being set to 0. The method then returns the remembered value of the balance. The following exercises will help illustrate why a local variable is needed here, as we try to write the refund balance method without one. It's quite common to initialize local variables within their declaration, so we could abbreviate the first 2 statements of refund balance as the following. But it's still important to keep in mind that there are 2 steps going on here. The first is declaring the variable amount to refund, and then secondly, giving it an initial value. But beware, a common pitfall is that a local variable of the same name as a field will prevent that field from being accessed from within a constructor or a method. When we get to chapter 3, you'll see that there's a way around this when it's necessary. So why not pause here and have a go at the following exercises. With the introduction of the amount to refund in the refund balance method, we have now seen 3 different kinds of variables: fields, formal parameters, and local variables. It is important to understand the similarities and the differences between these 3 kinds. So here's a summary of their features. All three kinds of variables are able to store a value that is appropriate to their defined types. For instance, a defined type of int allows a variable to store an integer value. Fields are defined outside of constructors and methods. Fields are used to store data that persist throughout the life of an object. As such, they maintain the current state of an object. They have a lifetime that lasts as long as the object lasts. Fields have a class scope. They are accessible throughout the whole class so that they can be used within any of the constructors or methods of the class in which they are defined. As long as they're defined private, fields cannot be accessed from anywhere outside of their defining class. Formal parameters and local variables persist only for the period that a constructor or method executes. Their lifetime is only as long as a single call, so their values are lost between calls. As such, they act as temporary rather than a permanent storage location. Formal parameters are defined in the header of a constructor or method. They receive their values from outside, being initialized by the actual parameter values that form part of the constructor or method call. Formal parameters have a scope that is limited to their defining constructor or method. Local variables are defined inside the body of a constructor or method. They can be initialized and used only within the body of the defining constructor or method. Local variables must be initialized before they are used in an expression. They're not given a default value. And local variables have a scope that is limited to the block in which they are defined. They're not accessible from anywhere outside of that block. New programmers often find it difficult to work out whether a variable should be defined as a field or as a local variable. The temptation is to define all of the variables as fields because they can be accessed from anywhere in the class. In fact, the opposite approach is a much better rule to adopt. Instead, it would be better to define the variables local to a method unless they are clearly a genuine part of an object's persistent state. Even if you anticipate using the same variable in two or more methods, define a separate version locally to each method until you are absolutely sure that the persistence between method calls is justified. So, in developing a better version of the ticket machine class, we have been able to address the major inadequacies of the naive version. In doing so, we have introduced two new language constructs, the conditional statement and local variables. A conditional statement gives us the means to perform a test, and then on the basis of the result of that test, perform one or the other of two distinct actions. And then local variables allow us to calculate and store temporary values within a constructor or a method. They contribute to the behavior that their defining method implements, but their values are lost once that constructor or method finishes its execution. You can find more details of conditional statements and the form that their tests can take in Appendix D. This chapter has covered a lot of new ground, and we have introduced a lot of new concepts. We will build on these concepts in future chapters, so it's important that you're comfortable with them now. So try the following pencil and paper exercises as a way of checking that you are becoming used to the terminology that we've introduced in this chapter. Don't be put off by the fact that we suggest that you do these on paper rather than within BlueJ. It will actually be good practice to try these things out without a compiler. So have a go at the following exercises shown here on the screen. So if you've managed to complete most or all of these exercises, then you might like to try creating a new project in BlueJ and making up your own class definition for a person. The class could have fields to record the name and the age of the person, for instance. However, if you're unsure how to complete any of the previous exercises, look back over the earlier sections of this chapter and the source code of the ticket machine to revise what you are unclear about. And in the next section, we will provide some further review material. By this point in the chapter, you will have met a lot of new concepts. To reinforce them, we shall now revisit a few in a different but familiar context. Along the way though, watch out for one or two further new concepts that we will then cover in more detail in later chapters. So open up the Lab Classes project that we introduced in chapter 1, the previous chapter, and then examine the student class in the editor. In this small example, the pieces of information that we wish to store for a student are their name, their student ID, and the number of course credits they have obtained so far. All of this information is persistent during their time as a student, even if some of it changes during that time, for example, the number of credits. Therefore, we want to store this information in fields to represent each student's state. The class contains 3 fields: name, ID, and credits. Each of these is initialized in the single constructor. The initial values of the first 2 are set from the parameter values passed into the constructor. Each of the fields has an associated get accessor method, but only name and credits have associated mutator methods. This means that the value of an ID field remains fixed once the object has been constructed. If a field's value cannot be changed once it's initialized, we say this is immutable. Sometimes we make the complete state of an object immutable once it's been constructed, and the string class is an important example of this. The getLoginName method illustrates a new feature that is worth exploring. We are seeing 2 things in action here. First, calling a method on another object, where the method returns a result, and second, using the value returned as a result as part of an expression. Both name and ID are string objects, and the string class has a method substring with the following header. The index value of 0 represents the first character of a string. So getLoginName takes the first 4 characters of the name string and the first 3 characters of the ID string, and then concatenates them together to form a new string. This new string is returned as the method's result. For example, if name is the string Leonardo da Vinci and ID is the string 468366, then the string Leon468 would be returned by this method. And we will learn more about method calling between objects in chapter 3. In the previous sections, we have seen various expressions to achieve various computations, such as the total plus price calculation in the ticket machine, and the name.substring expression in the student class. In the remainder of this book, we shall encounter many more operations, sometimes written with operator symbols, such as the plus sign, and sometimes written as method calls, such as substring. When we encounter new operators and methods, it often helps to try them out with different examples. So the CodePad, which we briefly used in chapter 1, can help us experiment with Java expressions. Here, we can type in expressions which will then be immediately evaluated and the results displayed. And this is very helpful for trying out new operators and methods. When the result of an expression in the CodePad is an object, such as a string, it will be marked with a small red object symbol next to the line showing the result. You can double-click this symbol to inspect it or drag it onto the object bench for further use. You can also declare variables and write complete statements in the CodePad. So whenever you encounter new operators and method calls, it's a good idea to try them out here to get a feel for their behavior. And you can explore the use of variables in the CodePad. For example, try the following. If you were to write sum equals 99 plus 3, you would see the following error message. Error cannot find symbol, variable sum. This is because Java requires that every variable, sum in this case, be given a type before it can be used. Recall that every time a field, parameter or local variable has been introduced for the first time in the source, it has had a type name in front of it, such as int or string. So in light of this, now try typing the following into the CodePad. Int sum equals 0, and then sum equals 99 plus 3. And this time, you'll notice that there is no complaint, because sum has been introduced with a type, and it can then be used without repeating this type thereafter. If you then type sum on a line by itself, with no semicolon, you will see the value that it currently stores. Now try this in the CodePad. String swimmer equals cat plus fish, and then swimmer. And then once again, we have given an appropriate type to the variable swimmer, allowing us to then make an assignment to it and then find out what it stores. And this time, we chose to set it to the value we wanted at the same time as declaring it. So what would you expect to see after the following? String fish equals swimmer, and then fish. Try it out. What do you think has happened in the assignment? So in this chapter, we have covered the basics of how to create a class definition. Classes contain fields, constructors, and methods that define the state and behavior of objects. Within the body of a constructor or method, a sequence of statements implements that part of its behavior. And local variables can be used as temporary data storage to assist with that. We've also covered assignment statements and conditional statements, and we'll be adding further types of statements in later chapters.